Yes, hi, my name is Bob Corey. Thank you, Hussein and Jim, and having this opportunity to celebrate the rich legacy of ITAMP. I am an ITAMP alum, going way back to the early days. I arrived here in 1991 as a pre-doc for 6 months. And it's such a great place. I stayed for 8 years. So I've always been very grateful to Alex and Kate for not kicking me out. And any opportunity to come back, I'm always very, very grateful to come back. So without further ado, our first talk is Nicole, younger Halpern. Whenever you're ready.
So first, I'd like to echo the earlier speakers in saying thank you. For instance, Hossein has always been such a really steadfast advocate for the ITAMP fellows. I was an ITAMP fellow here 2018 to 2021. Also, when I was here, former ITAMP fellows I would reach out helping hands and invite us to give talks. And also, I arrived here from Pasadena, but before I arrived, my possessions arrived from across the country. So Hannes was kind enough to sign for them when they arrived. So there were all these kind of notes of kindness and helping that made this feel like a family. And I also wanted to say especially thank you for intellectual support beyond career support and just support on a personal level. I do quantum thermodynamics. Quantum thermodynamics is a very young field that grew up while I grew up in my PhD. And Europe has been way ahead of the US in this field. So I was often the only American PhD student at quantum thermodynamics events. But in no small part, thanks to support by ITAMP, now quantum thermodynamics is a booming field across the world. It's growing a great deal in the US. This year, the ITAMP Winter School was actually the first quantum thermodynamics school to take place in the US. And in Maryland, we have now the first quantum thermodynamics hub in North America. So thanks for this support for an intellectual path that was a little unusual, but I felt really passionate about. Okay, now that that's said, I'd like to start on a subfield within quantum thermodynamics that's been growing up recently, and it was actually motivated by very basic undergraduate statistical mechanics. As undergraduates and throughout physics, we often hear there's some small system interacting with a big environment, maybe a quantum computer and the rest of the world. The two exchange things. If they exchange heat, the small system may thermalize to a canonical state. If they exchange heat and particles, the small system may thermalize to a grand canonical state, and so on and so forth for many different things that can be exchanged in different corresponding thermal states. This is in our textbooks. These things that are exchanged, like energy and particles, are conserved globally, so I'll call them charges. I'll denote them by Q and index them with A. It turns out that when we do quantum statistical mechanics, we usually represent these exchanged quantities with Hermitian operators that we implicitly assume commute with each other. This assumption is implicit. And think about your undergraduate statistical mechanics class. You probably didn't talk about this assumption. But the assumption turns out to lie behind, for example, derivations of the form of the thermal state, which is extremely basic, and the Onsager relations. But one of the most fascinating features of quantum theory is the importance of operators that don't commute with each other. So we're obliged to ask, what happens in thermodynamics when the dynamics conserve and exchange quantities that don't commute? This question motivated a small growing subfield that has grown up over the past few years. My group just published a perspective in Nature Reviews Physics on this little field. And this Brash stands for Billy Brash, who is a postdoc of mine. He's an NRC fellow and here today and tomorrow, so also feel free to ask him about this little subfield. Here's where I'd like to go in the rest of the talk. First, I'll give a simple example of such a system with non-commuting charges to put a picture in our heads. Then I'll talk about what in thermodynamics changes when charges stop commuting with each other, focusing especially on the eigenstate thermalization hypothesis, which is one of our best ways of understanding how a closed quantum many-body system thermalizes internally. Then I'll talk about what I think is particularly exciting at the frontiers of this little field is a puzzle that we've now come up with. Here's a simple example of a system we can keep in our heads. It was first proposed in this theory paper. The theory was realized in an experiment in Innsbruck by Rainer Bloch's group with trapped ions. And a generalization, I'm going to talk about qubits, but a generalization far beyond qubits is in this paper. So consider a chain of qubits. We can think of a small subsystem, maybe 2 of the qubits, as the system of interest. The entire system consists of n copies of the small system of interest, and the other copies form an effective environment. So the whole thing forms a closed quantum many-body system of the sort that's been studied theoretically and experimentally here at Harvard and elsewhere over the past several years. To introduce some natural charges, I'll denote by sigma aj the alphath component of the spin of qubit j. We can get global charges that don't commute with each other by taking the components of the spin and summing them across the lattice. We need dynamics, a Hamiltonian that has 3 properties. First, the Hamiltonian should conserve all of the global charges that don't commute with each other. Second, the Hamiltonian should take the charges locally and hop them between subsystems. And third, the Hamiltonian should be non-integrable if we want to give the system the best possible chance of thermalizing. We can construct such a Hamiltonian. We all know the form of the raising and lowering operators for the z component of the spin. And we all know how to form an operator that takes one quantum of the z component of the spin from site j plus 1 and hops it onto site j and does the reverse in superposition. And we can form analogous operators for the x and y type charges. So to form our Hamiltonian, we take our hopping operator, we sum it over the charges, then we sum over the lattice and introduce a hopping frequency. You might recognize this factor as the Heisenberg interaction. Very well known, can be simulated experimentally, although I should add that just within the past few years, it's turned out to exhibit some surprising anomalous transport properties, so it still has some surprises for us, perhaps. But I never see it written to show that it explicitly conserves non-commuting charges globally and transports them locally. But if you still find the Heisenberg model boring, you can step beyond it to, in a similar fashion, build up Hamiltonians that globally conserve and locally transport non-commuting charges via a technique in this paper. And if we want to make this Hamiltonian non-integrable to promote thermodynamic behaviors, we can either give the Hamiltonian interactions beyond nearest neighbor or make the lattice more than one-dimensional. So that's a simple model. We can keep it in our heads when thinking about what changes in thermodynamics when charges don't commute with each other. We've now built up a number of observations, so I'm going to present a few select observations. As I mentioned, 2 derivations of the thermal states form break down. Also, since the global charges don't commute with each other, they don't share an eigenbasis. So they don't necessarily share an eigenspace. And it's a shared eigenspace that can serve as a microcanonical subspace. Let me review what microcanonical subspaces are and why they're important in thermodynamics. Let's go back to the simpler problem in which the small system and big environment are exchanging just heat and particles. Suppose that we want to convince ourselves the small system really is in the appropriate thermal state. Then we'll suppose that the global system has a well-defined particle number. It's in an eigenspace of the total particle number operator and has a pretty well-defined energy. But we will attribute to the global system a microcanonical state. It's the projector onto this microcanonical subspace, normalized by the dimensionality of the subspace. But we trace out the environment to get the reduced state of the small system of interest, which turns out to be the grand canonical state, the appropriate thermal state, if the small system and big environment couple only weakly. This is in textbooks. Now, suppose we have more charges that commute with each other. The microcanonical subspace will be an eigenspace shared by those charges, other than the Hamiltonian, which is special because it generates the time evolution. But as we said, if the charges don't commute with each other, they don't share an eigenbasis, they don't necessarily share an eigenspace or many eigenspaces. So we don't have recourse to this microcanonical subspace. So we don't even have the first ingredient in this textbook argument for convincing ourselves that the small system is in a thermal state. So we shouldn't necessarily expect normal thermalization, which is unusual because thermalization is ubiquitous. It takes something special like many-body localization in order to stave off thermalization. Third, non-commuting charges cause the eigenstate thermalization hypothesis to break down. So let me provide a little bit of background about the eigenstate thermalization hypothesis. First of all, it contains a horrible number of syllables, so it's often abbreviated as the ETH. It's a toolkit used across many-body physics. I should point out, since this is an ITAMP reunion, that one of the seminal papers about the ETH was co-authored by Maxime Olshani, former ITAMP fellow. The ETH helps us understand how a closed quantum many-body system thermalizes internally in the following sense. We can take our favorite local operator and represent it with a matrix relative to the energy eigenbasis. The ETH is an ansatz for the form of those matrix elements. So suppose that we have an operator O and a Hamiltonian that obey the ETH. Suppose that the Hamiltonian is non-degenerate. And suppose that we start off the global system in one of these microcanonical subspaces. Then we can infer that internal thermalization happens in the following sense. So suppose that we measure the expectation value of this favorite operator at some time t, and then we average the expectation value over time. That time average equals the appropriate thermal average to within small corrections. Here, n is the size of the global system. So that's what thermalization means in this case. But if the charges don't commute with each other, the Hamiltonian will have degeneracies, thanks to Schur's lemma, to group theory. Also, we just established that we cannot rely on microcanonical subspaces. What about the ETH? Can we at least hold on to that postulate? Turns out no, because of the Wigner-Eckert theorem. I think probably to most physicists, the Wigner-Eckert theorem is something we learn on the way to qualifying exams in grad school, and then most people forget about it. Probably this is the best crowd in which to reference the Wigner-Eckert theorem because of its importance in AMO physics. It dictates selection rules in atomic transitions. Right? If we have an atom with some amount of angular momentum, and then a photon hits the atom, and we ask, what is the probability amplitude for transitioning to some other amount of angular momentum? The answer is given to us by the Wigner-Eckert theorem. But really, we can see the Wigner-Eckert theorem as dictating the forms of elements of matrices that represent operators relative to the energy eigenbasis. But that's what the ETH is supposed to do. It's a hypothesis for those matrix elements forms. But the Wigner-Eckert theorem is a theorem. It's been proved. It is true. Whereas the ETH is just an H. It's just a hypothesis. So the Wigner-Eckert theorem wins out against the ETH. And so we can't even rely on the ETH in the context of non-commuting charges. Okay, so do we have to give up one of our best frameworks for understanding quantum many-body thermalization? Well, not entirely. I had the privilege and pleasure, right after leaving ITAMP, of working with Mark Srednitsky's group. Mark Srednitsky was another one of the folks responsible for the ETH, to introduce a non-abelian ETH, consistent with non-commuting charges. And here I'm going to focus on charges that are components of angular momentum. In order to present this non-abelian ETH in full, I'd have to present a whole bunch of technical background, which I don't have time for in 25 minutes. So I'm just going to sketch what this ansatz looks like. On one side of the equation, we have an element of a matrix that represents our favorite local observable relative to an energy eigenbasis. On the other side of the equation, we have some coefficient that ensures that this ETH is consistent with the Wigner-Eckert theorem. This coefficient multiplies a sum of two terms. This diagonal term is non-zero only in blocks along the diagonal of our matrix. The off-diagonal term, kind of creatively, can be non-zero even off the diagonal. The diagonal term encodes average behavior of that expectation value of our favorite operator. And the off-diagonal term encodes how this expectation value fluctuates about its average over time. And these two terms incorporate an extra spin quantum number that is absent from the ordinary ETH. And this structure, if you're familiar with the ETH, you might kind of recognize it from the ordinary ETH. So we said that when we wanted to infer about thermalization using the ETH, we needed to assume the ETH and also assume that our system was prepared in a microcanonical subspace. So we've kind of fixed that problem with the ETH in the presence of non-commuting charges. But how do we fix this problem with not having recourse to microcanonical subspaces? So we can introduce approximate microcanonical subspaces, which generalize the ordinary thermodynamic notion. In an approximate microcanonical subspace, each charge has just a fairly well-defined value, since they can't all have sharply well-defined values simultaneously because of the non-commutation. So suppose that we measure one of the global charges, QA. We get some possible outcomes that we can imagine as being along the x-axis. And on the y-axis, I'll sketch a probability density. So in an approximate microcanonical subspace, this probability density for each charge should be peaked about the expected value, which is the analog of the total particle number in ordinary thermalization that leads to a grand canonical state. And this peak should be not too wide. So all of the global charges should have not too large variances. You might worry that preparing a system in approximate microcanonical subspace is difficult, but it turns out that we can use product states. So for instance, in that trapped ion experiment in Innsbruck, the group prepared their system in a particular product state in an approximate microcanonical subspace. All right, so suppose that we can now use our non-abelian ETH, and we can use our approximate microcanonical subspace. What can we learn about thermalization of systems with non-commuting charges? Well, we need to check a number of different cases. First, suppose that the magnetization is as large as possible. It grows like the system size. Then you can show that the time-averaged expectation value of our favorite operator will equal the thermal expectation value to within the same small corrections as usual. So we can recover something that looks like the ordinary results. Although I should add, the proof is much, much, much tougher. Usually it's about a page, and here a bunch of appendices were involved because we have all these different cases we have to check, basically because of Klebsch-Gordon coefficients that come from the Wigner-Eckert theorem. But now let's go to the opposite extreme. Suppose the magnetization is as small as possible. It's 0. We can show that the time average equals the thermal average just to within corrections that are polynomially larger in the global system size. So in a sense, the system might not thermalize as much as usual. This is under an assumption that we argue to be physically reasonable. I think this result is interesting for a fundamental reason and the possibility of an application. If the system isn't thermalizing as much as usual, since thermalization goes hand in hand with the arrow of time, it's kind of as though the system doesn't quite feel the arrow of time as strongly as most systems do. And second, if our system doesn't thermalize as much as usual, maybe it retains some extra information about its initial conditions, so maybe we can use these non-commuting charges for the sake of quantum memory. All right, so this leads me to our puzzle. Now, the community has a pile of evidence about things that happen, things that change in thermodynamics when charges stop commuting with each other. Some of these pieces of evidence point toward some sorts of enhancements of certain facets of thermalization, but we also have some evidence pointing in the opposite direction. So we have some evidence of enhancements of thermalization, some evidence of hindrances of thermalization. I'll start with the hindrances of thermalization, since we've seen some of these ideas already. We said Non-commuting charges invalidate two derivations of the thermal state's form. Non-commuting charges prevent us from being able to appeal to microcanonical subspaces and invalidate the eigenstate thermalization hypothesis. Also, suppose that you have two thermal states, say just a hot system and a cold system. You connect them so that energy can flow between them. Energy will tend to flow from hot to cold, and whenever energy leaves a system or enters a system, it produces entropy, which goes hand in hand with thermalization. You can imagine now that we have two thermal systems that have not only different temperatures, but also different analogs of temperature that correspond to the different charges. Whenever charges enter systems or leave systems, as the two systems exchange charges, entropy is produced. And the amount of entropy produced is reduced if the charges fail to commute. You can see there is a term that's negative that depends pretty explicitly on the commutator. And so if non-commutation of charges reduces entropy production, it kind of fights against thermalization. Also, suppose that we have just small local operations like 2-qubit unitaries, and we want to implement global n-qubit unitaries. If there's no restriction on the local operations we can perform, we can implement all of the n-qubit unitaries. This is why quantum computation is universal. But now, suppose that our local operations have to conserve some charges. And consider the set of all n-qubit unitaries that conserve the same charges globally. Turns out, using these local operations, we can no longer reach all of the n-qubit unitaries. And if the charges fail to commute with each other, the constraints are even stronger. So non-commutation of charges, in a sense, kind of prevents us from taking advantage of something like as much chaos as usual. We can't get a system state all around the available subspace as much as usual. Okay, so what about the evidence that non-commutation of charges in some ways enhances thermalization? Well, we can measure the entanglement entropy in the system and environment composites. The buildup of entanglement is an important part of quantum many-body thermalization. And non-commutation of charges increases the average bipartite entanglement entropy. So many-body localization has been studied a great deal at Harvard, for example. It is a regime of matter in which thermalization is slowed down a great deal. We're not sure if it exists in the thermodynamic limit, but at least at observable system sizes, this is an interesting phenomenon. You can take a many-body localized system and force non-commuting charges on it. They will destabilize the many-body localization, and so allow for a quick an easy transition to quick thermalization. Finally, some Hamiltonians have algebraic structures called dynamical symmetries. Dynamical symmetries single out some special operators and prevent them from thermalizing. Shayan Majidi, a student of mine who's about to graduate actually, found that if you force non-commuting charges on such a Hamiltonian, they eliminate dynamical symmetries, and so eliminate the protections on these operators that would otherwise resist thermalization. So all of these results technically don't conflict with each other because they were derived in different specific settings, but conceptually they clash. So now I think we have a really great opportunity to reconcile all these different results. Does the enhancement camp or the hindrance camp win out? You might be able to tell that I'm kind of voting for and hoping for the hindrance camp. Or how can we put together these different pieces of evidence to create a whole consistent picture? So basically, I think we need to go around to every feature in chaos and thermodynamics and ask, how does it change if charges now fail to commute with each other? So there's a lot of work to be done here. In summary, talks about this little growing subfield of non-commuting charges in quantum thermodynamics. We can take a common textbook undergraduate statistical mechanical setting, and we make one non-commutative tweak, our expectations about thermalization breakdown. We saw a simple example of a chain of spins and saw that a number of features of thermodynamics change. For example, the eigenstate thermalization hypothesis breaks down. And now we're left with a puzzle, and so lots of opportunity for future work. So this is the perspective that I mentioned earlier, but my group has been fairly obsessed with non-commuting charges for a few years, so this is all our work on the subject in case you're interested. And thanks for your time.
Thank you. Plenty of time for questions. Start with Timo.
Oh, hi. Very nice talk. Thank you. So I was just wondering if there is any insight into your problem that could be gained from just quantum theory of open systems, which you mentioned. But you know, there's this quantum Mbemba effect, where you have degeneracies and the thermalization slows down. And you mentioned degeneracies as a consequence of non-commuting operators. So that makes me think that quantum theory of open systems can have something to say. If you trace out your big system and you get your reduced density matrix, I guess by analyzing the structure of the bath, you can actually tell quite a bit, because there is rigorous proofs, for example, if you have a bosonic bath, that you have thermalization. Right? Like, so weak coupling, in the weak coupling limit, no matter what. So if you get something resembling like bosonic bath, you may be able to prove more, right? Or let's say you have a fermionic bath, which never thermalizes, right? So, anyway, so I'm just wondering if that could be, do you think it's a viable pathway?
Yes. As I mentioned, I think that we should go around to kind of all the results and also all the toolkits in thermodynamics and related subjects, and I consider open quantum systems to be very closely related, and ask what happens here if the charges fail to commute. So Dieter Jauch and his group of collaborators have done a little bit of work on modeling systems with non-commuting charges using Lindblad-Master equations, and they were focusing on the how large a fixed point space is available, and they argue that the space available is large, or can be different, of a different size in the case of non-commuting charges than in the case of commuting charges. And so if it's larger, maybe we could use it to store some extra information more stably. But I think that's just one approach, and there's a lot more to be done.
Because yeah, I mean, the steady state depends on your bath and the coupling system to the bath. That's the answer that open quantum system theory tells you. And so there's no general answer. It depends on the structure of your system, the structure of your bath, and on the coupling, right? And so by doing that, you can figure out the steady state. So canonical state is not necessarily the only one, or the most preferred one. So that's kind of like normal conclusion, right? So there's nothing surprising there.
Yeah, so I think they had some interest in information storage.
Right, that's right.
I think that was their approach.
Oh.
I think there's a question.
Isn't in principle wrong to think that you could formulate some generalized Gibson samples that would replace microcanonical distributions and account for the additional constraints or selection rules imposed by the non-commuting charges?
So one of the kind of earliest questions addressed was, does it make sense to write down a thermal states form? Since these derivations of the thermal states form break down. So E.T. James, in his Quantum 1957 paper, when formalizing the principle of maximum entropy, said in one paragraph, oh, this argument also works if the observables that we know about don't commute with each other. So that's the first mention I know of in history of non-commuting charges in a thermodynamic type setting. So that's a very information theoretic justification of writing down this state, which now we might call a generalized Gibbs ensemble. Although he doesn't actually assume that things are conserved, it's more, his argument more involves observables that we know about. And so around 2014, a number of us were thinking, well, is there a more physical reason, more physical justification for writing down a thermal states form? So one way you get the form of the thermal state is through this microcanonical argument. Again, we can't appeal to microcanonical states, so we define the approximate microcanonical states, and using some quantum information theoretic tools, argued it does make sense to write down the form of the thermal state that we would call a generalized Gibbs ensemble, or in quantum thermodynamics, we call it the non-Abelian thermal state. And so now one of the questions is, how close to this non-Abelian thermal state does the system get under true dynamics?
Okay, one more question?
So So regarding the thermalization of states with a finite magnetization, can you give a bit more intuition why magnetization slows down thermalization? And then you also have like these two different scalings with the system size, one for vanishing and one for finite, and somehow like and the scaling with the system size completely changed from 1 over n to 1 over square root n. So how is that like a little bit of like weak magnetization, and what does that mean? Like how does this transition?
There are 3 magnetization regimes to think about. One is, suppose that magnetization is extensive, so as large as possible. I talked about that. I said in this case we can prove that thermalization happens as much as usual, so the correction to the thermal prediction is like 1 over global system size. I also talked about the opposite extreme, so when the magnetization is 0, then we can derive, under an assumption we believe is physically reasonable, the scaling of correction to the thermal prediction, that's like 1 over the square root of the system size. I didn't say anything about the entire regime in between, which is a lot larger, because that seems to break up into even more cases. Again, the proofs here are much more complicated, in large part because of Clebsch-Gordon coefficients. So one opportunity is to look at that entire in-between regime. We think there might also be anomalous thermalization there. But again, we need to treat all these cases individually. And kind of what we wanted to show was somewhere thermalization happens as usual, somewhere it happens differently and less, or anomalously.
Okay, let's thank Nicole one more time.